So in this video, I want to take care of sort of the odds and ends with some of these questions in the test review, such as this one dealing with functional group. Now, right here, we're not going to do chiral carbons for this test review. This is chapter 13. If you're watching this at the time of the recording, summer of 2020, chapter 13 is not on test 2. It's test 3, so we'll deal with that later. Here I want to focus on functional groups. And really, it's just the functional groups in chapters 11 and 12. So it's not even all of them. Now, in this one here, carbon, 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 these two are alkenes with the carbon-carbon double bond. I have a double bond here, but it's an oxygen. And so in chapter 12, that's either an aldehyde or a ketone. A ketone is the one where there's carbons on either side of the structure. So this is a ketone. This one is also a ketone. Got a carbon there, that's a ketone. If it's an aldehyde, the carbonyl group would be at the very end of a chain, and there'd be a hydrogen coming off of it. Now the OHs, hydroxy groups. So hydroxy is a term for the OH, just the OH, the oxygen-hydrogen bond, okay? That group. When that group is bonded directly to just run-of-the-mill carbon, that is an alcohol, okay? Another alkene, and this is actually another ketone. Now, let me do some, so let me go ahead and use this as another topic to illustrate another topic, and this is alcohol classification. Right, this is primary, secondary, tertiary. It's really describing the degree of branching for the alcohols. And the way we approach this, if you can imagine sort of focusing in on the functional group and then saying, well, there's a carbon there and there's a carbon there. There's 1, 2 carbons. This would be a secondary alcohol. And notice I'm not going any farther than the carbons that are bonded directly to the functional group. Doesn't matter how complicated everything else is, what's happening right around it. Another thing to know about a secondary alcohol is that there's 1 hydrogen attached to that carbon. This one up here, if I do the same thing, box in the functional group, and there's 1 carbon attached to it. Again, it doesn't matter how complicated everything else is around it, it's just that one little point. This is a primary alcohol. Primary alcohols have 2 hydrogens bonded to the carbon of the functional group. Now, some of these questions are just like open-ended questions. The key is posted on Moodle for this. Let me just address a few little things here. So when I talk about constitutional isomers of hexanal, well, what is hexanal? Hexanal is 1, 2, 3, 4, 5, 6 with the aldehyde group at the very end there. And so when I talk about constitutional isomers, that's where you start branching this thing. You can move the functional group around. Like for example, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So I can have a couple of different ketones. Like this would be 2 hexanone. Or I can keep the aldehyde group intact and then just branch this part here. So instead of 6 carbons, let's like go to 5. 1, 2, 3, 4, 5. Keep my aldehyde group right there. And then I have 1 carbon left over, and I can put that really any place on this interior portion of the chain. This would be 2-methyl pentanal. So really, when you talk about constitutional isomers, aldehydes and ketones are constitutional isomers of each other. Another one dealing with constitutional isomers is this kind of question. There's a couple of layers here, like one thing, so 6 carbons again, hexanol, 1, 2, 3, 4, 5, 6. And remember, so hexanol, the OH group is at the number 1 carbon because 1 is implied in this name. So if I want to put an OH group on one of the ends, I don't just want to do that. That's incorrect. 1, 2, 3, 4, 5, 6. I actually want to draw another line and do that. Okay, so great. That's hexanol looks like that. I still haven't answered the question. Anyway, now what I need to do is actually I have an OH group. I not only have to move it in the middle here somewhere, but also have to branch around that middle to where there's 3 carbons attached to the carbon of the alcohol functional group. So what that's going to look like is something like 1, 2, 3, 4. Actually, I can go 5. OH and then 1 methyl group. All right, that is a tertiary alcohol. I sort of box in my functional group and I say, well, there's 1, 2, 3 carbons to that one. Name of this guy would be this is 1, 2, 3, 4, 5, 2-methyl, 2-pentanol. And then to get a second tertiary alcohol, I can just take this group, the methyl group and the OH, and I can just move it to this carbon. 1, 2, 3, 4, 5, methyl group, OH group, and then this would be 3-methyl, 3-pentanol. So again, this is tertiary alcohol, and then this is a tertiary alcohol. That guy there, that's a primary alcohol, right? Because that's the carbon that's bonded to the alcohol, and then there's just 1 carbon attached to it. A little bit about polarity and solubility of these different compounds. If a polar organic compound is soluble, that means the carbon chain is short. So let's just make it easy for ourselves. Right? What's the shortest alcohol you can have? Is methanol. And I open it up like this because I'll use it to talk about, the other questions here. If I have something that's insoluble, so, all of those functional groups we saw in chapter 12, alcohols, or at least the main ones we're talking about here, alcohols, aldehydes, and ketones, they're all polar. And so that does allow them to be at least somewhat soluble in water. But it's a function of the size of the carbon chain. If I want something that's insoluble, like for an alcohol, like 7, 3, 4, 5, 6, 7, that would be insoluble. Basically, the polar portion is, or the nonpolar portion of the molecule is too big. The polarity here cannot bring it into solution for in the water too well. Now, if I want to go in, I won't do both. I'll just do the alcohol here. Remember the notation where we try to describe the polarity of a system? Right, we have electronegative oxygen. It's going to be the delta negative, right? It's pulling electron density toward itself. So that means that whatever it is directly bonded to is going to be a little bit electron deficient. So in this case, a delta positive here, and also a delta positive there. For our class, we keep it simple, and we don't, even if the chain was longer. Like here, I guess I will be doing it here. That's a delta negative, and that's a delta positive. We're only worried about the bond the atom directly to the electronegative atom. We're only concerned with the atom that's directly bonded to the electronegative atom. The effect is felt farther downfield, but we're not worried about that. And then if we want to, see how water is going to interact with it, well, what is water? Water has this formula. It's also polar, so it has that delta negative, delta positive, delta positive. And then what happens? There's this interaction. Right? In our universe, for whatever reason, negative and positive are attracted to each other. And we call that a hydrogen bond. I'm adding more to it than what the question is asking for, but this is a review. We want to talk about a few other things. Last one I want to do here is this one. Again, this is chapter 13. So that's for later test review. This is a formula for an alkene. Right? Has that ratio. You can see it there. Diastereomer, that's associated with alkene as well. Right? That's where you have the cis trans. So if I want 7 carbons that can show the cis trans, well, let's just stick with bond line structure. First the trans, then the cis. So the trans is just a normal zigzag in the bond line structure. 1, 2, 3, 4, 5, 6, 7. And I'm going to choose to put the double bond at the number 2 position here. So this would be 2, or I should say trans, 2 heptene. Now these diastereomers, remember they have the Same molecular formula. They have the same structural formula, meaning the double bond is the number 2 position. They just have a different spatial arrangement. And it's probably easier to look at the hydrogens. That's, for this class, that's certainly the atoms that show up most of the time. Not always, but most of the time. These hydrogens are on opposite sides of the structure. One's on top, one's on bottom. That's trans. If I want to do cis, the 2 hydrogens go on the same side. So it's basically a hydrogen here and a hydrogen there, where that zigzag is. So in the cis arrangement, the zigzag goes down like that. Now, to make that look, normal on a piece of paper, 7. 1, 2, 3, 4, 5, 6, 7. So again, let's ink in the hydrogens, which, this structure is fine. This is actually the correct structure. But I'm going to ink this in just to try to illustrate. Again, it's like that bond and that bond, right? It's that. If I was doing the normal zigzag here, it would be something like that. But instead of a carbon sitting there, it's that hydrogen. And so what happens, it puts this bend in the structure. And this bend is permanent for this alkene. Again, I said same molecular formula, same structural formula, and that can actually be seen in this portion of the name. Right? Both of these are 2-heptene, 1, 2, 3, 4, 5, 6, 7. The difference is a spatial arrangement, trans versus cis. Last little topic beyond this, if I had done this, so 1, 2, 3, 4, 5, 6, 7, and instead of putting the double bond there, 1, 2, 3, if I put it on the 3rd position, these two, they're not diastereomers. I actually have a different structural formula at this point. These two are constitutional isomers, or structural isomers. Sometimes you hear that phrase used. So this would be named trans 3-heptene. Okay, so a little pattern. This portion of the IUPAC name is going to be identical when you're dealing with cis-trans. This portion of IUPAC name is going to be different when you're dealing with constitutional isomers. Just a little pattern may be helpful. But that's all I got. Thanks.